Hello, and welcome to my lab report number 5 for the Physics 2 class in the spring 2019 semester. Today we will be going over the Faraday's Law lab. The objective of this lab was to model and predict the amount of time for a magnet to fall through a conducting loop, creating an opposing magnetic field, and compare it to experimental results. In order to do this, we will be using an aluminum foil in a bar magnet, and we would measure the amount of time required for the magnet to fall to model and quantify the magnetic force being caused. In order to do this, we will be using some fundamental physics principles. First and foremost, we will be using Faraday's law, where the electromotive force is equal to the negative rate of change of the magnetic flux with respect to time, given here in yellow. And also we will be using the concept of magnetic fields, more specifically the Biot-Savart law for the magnetic field being created by a point charge at a given observation location, given here in white. Thirdly, we will also be using Newton's second and third law. We will be using Newton's second law in order to determine the force being caused on the magnet by the loop. And then we will be using Newton's third law to determine the net force on the whole system. So in order to do this lab, we first had to acquire some real-world data. We used an aluminum foil of length 29 centimeters and with thickness of 1 centimeter. It had an in-ear radius of 1.6 centimeters. And then using video editing equipment, we measured that the average time for the bar magnet to fall through this aluminum foil with the north pole pointing towards Earth was 2.43 seconds. And then using some numbers from previous labs, such as the dipole moment calculated for the bar magnet in lab 3, we will be modeling the rest of this experiment. So in order to model this, we did some coding in CloseScript. What we would model is we would use multiple loops representing the aluminum foil, each one with its own independent current. And then here in the image you can see in red and blue, that's representing the bar magnet falling through the aluminum foil. And some observations we can make based on this model and using all of the numbers we crunched from the last slide were that the velocity while falling through the aluminum foil was constant, and also it was less than it would be if the bar magnet was simply in free fall. So therefore there must have been a force opposing the fall of the magnet. So some of the things we can ask ourselves after modeling these situations are the following. For example, what if the resistivity of the conductor were reduced as close as possible to zero? So we know resistivity is proportional to resistance, and we know that that current is equal to the electromotive force over resistance, therefore it's inversely proportional to resistance. So if the resistance is going towards zero, the infinity is going, it's trending towards infinity, but rather it's getting rather big. And then if the current is getting rather big, since the force on the magnet depends on the current, we can say that the motion of the magnet is going to be affected in that since the force is getting bigger, the velocity of the magnet would be getting smaller, so it's going to take a longer time for the magnet to fall through the aluminum foil. And then secondly, what if holes or slots were cut into the tube? Well, we know that the opposing force is being caused by the induced current. Therefore, at places where there's holes, we would have none of the conducting aluminum foil and therefore no induced current. So at these points where there's a hole, there would be no opposing force, and therefore the magnet would fall faster through these slots, and overall it would fall faster through the aluminum foil. So yeah, that's all I have for lab number 5, and thank you for watching.